Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I'm Philip Emeagwali. What is Philip Emeagwali known for? I'm known for discovering practical parallel supercomputing and for discovering that vital supercomputer technology across a global network of processors that outline and define an internet. That was how I invented a new internet that I visualized as a small copy of the internet. My new internet tightly encircled the globe in the manner the internet does. But my supercomputing was around a globe, not around the globe. I was the first supercomputer scientist that could solve the toughest problems arising in science, engineering, and medicine, and solve them by parallel processing them across millions of processors that tightly encircled a globe as an internet. The proof of principle lecture that foreshadowed my discovery of practical parallel supercomputing took place in November 1982 in an auditorium near the White House in Washington, D.C. My experimental discovery of practical parallel supercomputing and my discovery of how to solve grand challenge problems and solve them across millions upon millions of tightly coupled commodity processors was a new knowledge that changed the way we looked at the supercomputer. That was the new knowledge that opened the door to extreme scale computational science that redefined the boundaries of physics and mathematics. The moment and place of that discovery of practical parallel supercomputing was 8:15 in the morning of July 4, 1989 in Los Alamos, New Mexico, United States. I remember that date because it was also the US Independence Day. I celebrate my 4th of July as the quote-unquote Independence Day, or the starting date of the modern supercomputer that solves millions upon millions of problems at once and solves them by chopping up a grand challenge problem into a million less challenging problems and then parallel processing that million problems by mapping and solving each initial boundary value problem and doing so with a one problem to one processor correspondence. That was how I discovered that the massively parallel supercomputer will become the vital technology that will enable us to solve otherwise intractable grand challenge problems and solve them while respecting the laws of physics that were embodied into that problem and define it as an initial boundary value problem. After that discovery, the parallel supercomputer became commercialized, and today the end user's market is $20 billion a year. That first application of massively parallel supercomputing revealed how to compute the weather above and below the surface of the earth, as well as pushed the frontiers of knowledge of computational physics, computational mathematics, and computational medicine. In addition to discovering how to compute faster, parallel supercomputing contributed to our greater understanding of extreme-scale computational sciences and engineering. After my 4th of July 1989 discovery, parallel processing left the laboratory and entered into the granite core of every supercomputer that is manufactured today. Parallel supercomputing is harnessed to solve the grand challenges of science, such as your evening weather forecast. Parallel supercomputing created a new paradigm in the way we use the modern supercomputer. The metric for measuring the impact of this scientific discovery is that the parallel supercomputer market is upward of $20 billion a year. The supercomputer of today is used to discover and recover otherwise elusive crude oil and natural gas that was for 1 million years and buried 1 mile deep below the surface of the Niger Delta oil fields of the southeastern region of my country of birth, Nigeria. Parallel processing represents a major breakthrough that changed the way we look at the supercomputer. My experimental discovery of practical parallel processing that occurred on the 4th of July 1989 was the starting point of the modern supercomputer that parallel processes across processors. From the 1940s through 80s, the technology of parallel processing that underpins the modern supercomputer was mocked, ridiculed, and dismissed as a blue sky thinking that was not grounded in mathematics, namely calculus or algebra or logic. Back in the 1980s and earlier, parallel processing was rejected as a useless technology that was not in touch with the physics of grand challenge problems. So for the 67 years onwards of its first mention as a science fiction story that was published on February 1, 1922, research in massively parallel processing was ridiculed and mocked as a huge waste of everybody's time. My earliest research reports on parallel processing were rejected in December 1980 and in September 1983. In the early 1980s, parallel processing was rejected as blue sky research that could not be used to solve grand challenge problems arising in STEM fields. But for me, and in the 1970s and 80s, parallel processing was a curiosity-driven supercomputing research that had the clear goal of discovering how to solve the toughest problems arising in STEM fields. My research goal was to invent how to solve those grand challenge problems and solve them across the millions upon millions of identical processors that were married to each other as one cohesive virtual supercomputer that is a new internet de facto. Until my experimental discovery of practical parallel processing that occurred on the 4th of July 1989, it was said that parallel supercomputing has as much societal value as a patch of blue sky. That was the reason I was the only full-time programmer of the 1980s of the most massively parallel processing machinery ever built that was then a supercomputer hopeful. That was the reason I was referred to as the first parallel supercomputer scientist. I am an extreme skilled computational mathematician that came of age in the 1970s and 80s. In the 94 mathematics subject classifications of the American Mathematical Society, I worked in 7 of those fields, namely partial differential equations, finite differences, numerical analysis, fluid mechanics, geophysics, information and communications technology, and computer science. To invent practical parallel processing meant that I had no teacher that taught me the parallel supercomputer. As the first supercomputer scientist, I was the only person that could deliver a proof of principle lecture of how to parallel process across a new internet that is a new global network of 64 binary thousand processors that were identical to each other and that were equal distances apart from each other and that shared nothing between each other. It was a tradition that dates back to 17th century Isaac Newton through 20th century Albert Einstein to invite a physicist that made a new discovery to share his new knowledge with the scientific community. I gave several lectures on my new discovery of practical parallel supercomputing. After 16 years of parallel supercomputing across up to 65,536 processors, that was a world record in the 1980s, I became the most knowledgeable person on massively parallel supercomputing. I was the first person to deliver extensive lectures on massively parallel supercomputing. After parallel supercomputing for 16 years, I acquired the command of materials that enabled me to speak on how the newly emerging technology pushed the frontiers of knowledge and speak without notes. Vector supercomputer scientists that were continuously reading from their sometimes borrowed notes and reading from textbooks that were written by a different person had to read because they had never programmed a massively parallel supercomputer. If I delivered my supercomputer lectures from such borrowed notes, I would have been perceived as less intelligent and not credible and not the inventor of practical parallel supercomputing. Once again, I did not learn practical parallel supercomputing. By definition, it was impossible to learn the then non-existent technology and learn it from any practical parallel supercomputer textbook that was also non-existent. I invented practical parallel processing as the vital technology that makes supercomputers super. In the 1970s and 80s, parallel supercomputing was the misunderstood technology that many computer scientists hoped will forge a path to the world's fastest supercomputer. Until I forged that path and did so on the 4th of July 1989, supercomputer scientists did not have the experimental evidence to prove that parallel processing can be harnessed and used to solve the toughest problems arising in STEM fields. As the first parallel supercomputer scientist, I was the first person that gave a first-person account of how I figured out how to harness an ensemble of 64 binary thousand processors and use them in a one processor to one problem correspondent manner and use them to solve as many initial boundary value grand challenge problems arising in mathematical physics and beyond. I was the first parallel supercomputer scientist, and for that reason, I was the only parallel supercomputer scientist that recorded lengthy lecture series and did so in the first person singular and shared them as 1,000 YouTube video lectures. In the developing world, as well as in academia of the Western world, the scientific research is by necessity a tabletop experiment, such as computational fluid dynamic simulations on a desktop computer. In contrast, the speed of computing at the frontier of knowledge of supercomputing is 1,000,000 or 1,000,000,000 times faster than the speed of your computer. Scientific research is a large team effort. The prominent scientists of the 21st century get credit for team research. A physics paper that was published in Physical Review Letters was co-authored by 5,154 research scientists. Some of those co-authors were deceased. Only 9 pages of that research paper described their contributions to physics. The remaining 24 pages listed the names of the contributors. In contrast, I got credit for the practical parallel supercomputing that I invented alone. That is the reason Philip Emeagwali is the only supercomputer scientist that is the subject of school reports on the contribution of parallel processing to the development of the computer. I will never forget the date, July 4, 1989, the day I saw a new computer that no one else had seen, and the day that I discovered that new computer to be 65,536 times faster than the old computer, and the day that I discovered how to use that new computer to solve once impossible to solve grand challenge problems of science. I was in the news in 1989 because I was the first person to invent a new computer and do so alone, and to invent it unsupported. My technological achievement in 1989 that won the top prize in the field of supercomputing was a one-man battle against the new Mount Everest, namely the 25,000 vector supercomputer scientists of the 1980s that did not believe that parallel supercomputing will be useful. I'm Philip Emeagwali. I'm known for discovering parallel processing as the technology that defines every supercomputer. Parallel processing is expected to become the vital technology that will power every computer of the future. The supercomputer is the tool that must be used to massively parallel process the grand challenge problems facing humanity. The research on how to parallel process across 64 binary thousand human computers, or across as many electronic computers, or across as many processors, stalled for 67 years onward of February 1922. The date human parallel processing was first published as a science fiction story. Parallel processing stalled because no supercomputer scientists could figure out how to solve initial boundary value grand challenge problems that arose in science, technology, engineering, and mathematics. My contribution to the development of the supercomputer is this. I figured out how to solve a grand challenge problem of mathematics and physics, and how to solve such problems by chopping each into one binary million or one binary billion smaller problems, and then parallel processing the smaller problems across a new internet that was a new global network of one binary million or one binary billion processors that were identical to each other and that shared nothing between each other, with each processor operating its own operating system. On the 4th of July 1989, I figured out how to solve that grand challenge problem of mathematical physics. My discovery of how to parallel process the toughest problems changed the landscape of supercomputing, with every supercomputer now parallel processing. My discovery of practical parallel processing yielded an explosive surge in supercomputer speeds. My discovery of practical parallel processing paved the way for the modern supercomputer that is powered by up to 10 million commodity off-the-shelf processors. Years after the rejection of my discovery of practical parallel processing, the naysayers changed their story and explained that they did not understand how I parallel processed and solved the grand challenge problem of science. It is expected that parallel processing will enter into every computer. Worldwide, there are over 2 billion computers that could be parallel processing to become faster. That is, parallel processing should become the vital technology that will make computers faster and that could benefit everybody.
Insightful and brilliant lecture.